Have you ever wondered if there's some kind of secret pattern hiding inside completely random events? I mean, it sounds impossible, doesn't it? How can you possibly predict something that by its very nature is random? Well, it turns out under the right conditions, you actually can. So how on earth is that possible? Let's take a look. Okay, so let's think about some things that seem totally disconnected. For instance, the number of phone calls that hit a switchboard in any given 5-minute window. Or, what about the number of cars that pass a certain spot on a highway every minute, assuming traffic is flowing freely? We could even talk about the number of tiny misprints you might find on a single page of a book. All of these feel unrelated, totally unpredictable. But are they really? Well, here's the thing. These random, independent events, they often follow a hidden, predictable pattern. And the key to unlocking it is a surprisingly elegant little tool from the world of statistics. So, the tool that solves our mystery is called the Poisson Distribution. It's named after this brilliant French mathematician, Simeon Denis Poisson, and it's designed for one specific job, modeling the number of times an event happens within a set interval of time or space. Okay, I know what you're thinking when you see a formula like this. But seriously, don't let it scare you. Think of it less like complicated math and more like the secret code that describes this hidden pattern. This is what lets us figure out the probability of seeing an exact number of events. Like, what are the odds of getting exactly 3 phone calls in the next 5 minutes? Not 2, not 4, but precisely 3. And the secret ingredient, the one piece of information you need to make this whole thing work, is this Greek letter right here, lambda. So what is this mysterious lambda? It's just the average number of times the event happens in that interval. Yep, that's it. If you know the average, you can start predicting the probabilities. All right, so theory is great and all, but let's get our hands dirty and see how this thing actually works. Let's try to crack a real-world case. So here's our scenario. We've got a taxi company, and they know that on average, they get about 4 requests for a ride every half hour. That's our starting point. Our average, our lambda, is 4 for any 30-minute window. You can see how knowing this would be super important for managing their cars, right? And this is where the magic happens. What if we want to look at a different time frame, let's say a full hour? Well, as you can see in step 2, we just adjust our average. If we get 4 demands in 30 minutes, it's pretty logical we'd expect 8 in an hour. So our new lambda is 8. Now for step 3, we just plug that new lambda into our formula to find the probability of getting exactly 1 demand. And the calculation in step 4 gives us the answer. There's only about a 0.3% chance of getting just 1 call in that hour. It's a tiny probability, but the key is we can now put a precise number on it. But just like any good detective's tool, you can't just use it for everything. There are rules to the game. The Poisson distribution only works under a very specific set of conditions. So let's check out the investigator's rulebook. For this tool to really work, 4 things have to be true. First, the events have to be random. Second, they have to happen one at a time, singly. 2 phone calls can't arrive at the exact same nanosecond. Third, and this one is super important, they have to be independent. One event happening can't make the next one more or less likely. And finally, the average rate has to be constant. You can't really compare rush hour traffic with 3 a.m. traffic. And this slide right here is a perfect way to understand that independence rule. Free-flowing traffic on a bridge, that's a great model because all the cars are moving independently of each other. But a line of cars waiting to get into a parking garage, that's a terrible model. Why? Because the cars are completely dependent on each other. Nobody moves until the car in front of them moves. All right, now for the final reveal. This is my favorite part. There is one incredibly cool property of the Poisson distribution that's basically like a statistical fingerprint. It's a way we can check if our model is a good fit for the data we're looking at. So let's go all the way back to our first example, the phone calls at a switchboard. Here's some real data collected over 100 different 5-minute periods. You can see that in 71 of those 5-minute chunks, not a single call came in. Now, if we take all the calls from that table and we average them out over those 100 intervals, we get our mean. That number, our lambda for this specific case, is 0.37. Okay, next, we calculate something called the variance. Now, all variance really is a measure of how spread out the data is. Are the number of calls pretty close to the average most of the time, or are they all over the map? For this data, the variance is 0.4331. And here it is, the aha moment. For any set of events that perfectly follows a Poisson distribution, the mean and the variance are equal. Now look at our numbers. They're not identical, but they are incredibly close. This is the fingerprint. This is the final clue that tells us, yes, the Poisson distribution is a fantastic model for the seemingly random data. So we started with a mystery, how to predict randomness. And we found a pattern, a formula, and even a statistical fingerprint to confirm it. From radioactive decay to the number of customers arriving at a store, this pattern is hiding in plain sight all around us. So the only question left is, now that you know what to look for, where are you going to see it next?